This is the last day for section 14.1. We are going to be using mathematical induction to prove statements about factors. So we're still going to use our same formal setup for our proof, but our proof is going to change slightly because the statement is a little different. So here it says, use mathematical induction to show that the statement is true for all natural numbers. 23 to the n minus 1 is divisible by 11. So let's start first with our base step. So we want to show that P of 1 is true. And so P of 1 is that for n is equal to 1, 23 to the first power minus 1, which is equal to 22, is in fact divisible by 11. So we've proven that P of 1 is true. Now for our inductive step, we're going to assume that P of k is true, and we want to show that P of k plus 1 is also true. So I'm going to write this as an if-then as well. Now for the if-then part, we have to be able to come up with an equation for this. Okay, 23 to the n minus 1 is divisible by 11. Well, this is what you're going to do whenever you're asked to show that something is divisible by something, or something is a factor of something. You're going to rewrite it a little bit differently. If we multiply 11 by any constant, let's call that constant C1, well then that's going to equal 23 to the n minus 1. So I'm actually going to replace this n with a k, because we're assuming that P of k is true. But this is how I can write that as an equation. Now, my then statement should be that 11 times some other constant should equal 23 to the k plus 1 minus 1. So now we're going to work on the left-hand side here, or this left part here, the if statement, and try to make it look like the right-hand side here. So let's start with 11 times our constant equaling 23 to the k minus 1. Now, just like I talked about before, we want to try to match the exponent side. That's going to be the easier to deal with. So to match the right-hand side, this is the side with the exponents, I'm simply going to multiply by 23 so that I can match that exponent side. So I'm going to take both sides here, multiply by 23, and so I end up with 253 times that constant is equal to 23 to the k plus 1 minus 23. Okay, so now from here, I want to try to match the right-hand side. So taking a look at this right-hand side here for both of these, I notice that they differ by negative 22. So I'm going to now add 22 to both sides so that I can get the right-hand side at least to match. So now I'm left with 23 to the k plus 1 minus 1, and on the right-hand side, 253 times that constant plus 22. So again, all that I did was I added 22 to match the right-hand side here and here. Alright, now that I've done that, I want to work now on the left-hand side. I'm going to factor out an 11 here, and now I'm going to write this as 23 times that constant plus 2 is equal to 23 to the k plus 1 minus 1. Okay, now here's the weird part, because I think everything so far has been pretty easy to understand algebraically. Now, this term here, 23 times c1 plus 2. Now remember, this is just a number times another constant, another number plus another number. So this is really just a constant. Okay, so 23 times c1 plus 2 is simply a constant. So I'm going to replace this constant with another constant. So this is the big trick here, is to replace it. So now I have 11 times some other constant, we're going to call that c2, equaling 23 to the k plus 1 minus 1. Now, if you take a look at this last statement here, that actually matches what we're trying to prove, p of k plus 1. So because p of k plus 1 is true, then we know that all p of n must be true as well. So p of n is true for all natural numbers. Okay, if you feel comfortable enough with this, you can try the next question on your own. I'm going to work through now problem 2 with you. So here it says, use mathematical induction to show that this statement is true for all natural numbers. 2 to the 2n minus 1. 2 to the 2n minus 1 is divisible by 3. So let's start with our base step. For p of 1, let's show that this is true. So p of 1 for n equals 1, and we have the statement 2 to the 2 times 1 minus 1, which is equal to 4 minus 1, which is 3, is in fact divisible by 3. Now for our inductive step, we want to show that if p of k is true, so we're assuming, this is our assumption statement here, assume that p of k is true, and we want to show that p of k plus 1 is also true. So here we have another if-then statement. We have our if and our then, so let's work on both of those. Now remember, we want to turn this into an equation and write this expression here and kind of make this into an equation, so we know that 3 times some constant should equal 2 to the 2n minus 1, and of course I'm going to replace that n here with a k. So 2 to the 2k minus 1 is now my new expression here. And my then statement, what I want to show, p of k plus 1, will be that 3 times another constant is equal to 2 raised to the 2 times k plus 1 minus 1. Oops, I wrote this one over here backwards, sorry. This is minus 1. There we go. Okay, now, I'm going to simplify this and write this as 2 to the 2k plus 2 minus 1. Alright, now, let's work using our assumption and try to make this match what we're trying to prove. Alright, so we're going to start with this. Now, I'm going to try to manipulate the right-hand side here because I want to get the exponent side to match, and this is the easier one to deal with. But if I just multiply by a 2 here, and I distribute that 2, then I'm just left with 2 to the 2k plus 1 minus 2. Okay, so that's actually not going to match my exponents here. So instead, I will multiply by 2 squared. So that will match my my exponents then, at least. So I have 2 squared times 3 times that constant equaling 2 squared times 2 to the 2k minus 1. And if I simplify here, I'm left with 2 to the 2k plus 2 now, minus 2 squared, which I'm going to simplify and write that as just 4. So the right-hand side here is 4 times 3, 12, times that constant. So, or I'm sorry, the left-hand side. Now the right-hand side is what I'm focusing on, and I'm trying to make it match to this statement here. And I notice that these differ on the right-hand side now by just a 3. So since this has negative 3 more, I guess 3 less, I should say, than the right-hand side over there, I'm going to add 3 here on both sides. So now I'm left with 12 times that constant plus 3 equaling 2 to the 2k plus 2 minus 1. So now I'm noticing that my right-hand sides match. So this side here now matches this right-hand side as well. So that's a good thing. Alright, now on the left-hand side we have to work on that, so we're finished here. We're not going to manipulate that side anymore. But on the left-hand side, I'm going to factor out this 3 and write that as 4 times c1 plus 1 equaling, and again I don't touch that right-hand side. And so here's where you're going to use that trick again. Notice that 4 times c1 plus 1 is really just a constant. Okay, so 4 times c1 plus 1 is a constant, and we are going to simply replace it with a new one, and let's call that new constant c2. So we have 3 times c2 2 is equal to 2 to the 2k plus 2 minus 1, which is what we were trying to show all along. And therefore, since p of k plus 1 is true, p of n is true for all n. Okay, so you can kind of see that there's a very similar method for solving these, or writing these inductive proofs. So nice job. I will see you in class tomorrow.